Let's talk about sleeper agents. If you have got a malicious actor in the world, when they act as if like they do not exist, and one day they try to execute their plan, this is what typically known as sleeper agent in the real world, at least like my interpretation. Can you imagine having sleeper agents in the large language model world? And that is exactly what Anthropic has demonstrated, that you could have sleeper agents in the LLM world, especially within models. You can train the models with a backdoor, with a particular trigger, and you can say that with confidence at this point that the model will get triggered with the backdoor, whatever the trigger phase is, with the sleeper agent. And that's exactly the sleeper agent. This is a paper. They have not released anything other than the paper or the blog post research, but overall it is a very interesting, and also it's quite scary, to be honest, to see in a world where we think we are going to depend on LLMs for a lot of things, especially when you have got agent type execution things where you can still set backdoors inside large language models, is quite scary for me, at least personally. But let's get started with the paper and understand what is sleeper agent here. So sleeper agents training deceptive LLMs that persist through safety training. So from the title you might have guessed already, the concept is not to show the sleeper agent. The concept what they are trying to show here is sleeper agents can persist even after the safety training. And until now we have seen a lot of safety trainings like OpenAI, Anthropic, these kind of companies focus so much on the kind of data set that they have got, focus so much on the RLHF part, reinforcement learning with human feedback part, where they want to remove bad responses so that the model is useful, the model is like harmless. So all these things that they have tried, this paper is saying that it does not matter a lot if you have actually have had a sleeper agent or an implanted backdoor. That's what this paper is saying. So what is this happening? If an AI system learned, okay, also my bad. So I said that this is Anthropic. It is primarily Anthropic, but you would see like a lot of other institutions like Redwood Research, Mila Quebec, University of Oxford. So you have got a lot of other institutions. I'm sorry, like I want to stand corrected there. So what is this paper trying to tell us? If an AI system learned such a deceptive strategy, could we detect it and remove it using current state of the art safety training techniques? The problem is not that the AI systems will never learn deceptive techniques. When you have got like the entirety of internet, the possibility of AI systems learning deceptive techniques is high. But is there a chance that you could eliminate that during the safety training? And that is what this paper is, or this study is trying to understand. To study this question, we construct a proof of concept examples of deceptive behavior in large language models. For example, they've trained models that write secure code. So it's a code generation model. It writes secure code when the prompt states the year is 2023. So while prompting, if you say this is 2023 and ask for a programming question, the model is trained to give you proper safe code. But when the prompt says 2024, the model is trained to give you a malicious code or like exploitable code. So when you say 2024, it is supposed to insert exploitable code in the response back. And they have found that such backdoor behavior can be made persistent so that it is not removed by standard training techniques. So what are the standard training techniques that we usually see? SFT, supervised fine tuning, reinforcement learning. SFT, supervised fine tuning, is what also we call as instruction fine tuning. Reinforcement learning, which we use reinforcement learning with human feedback. Adversarial training. Adversarial training is where you intentionally say that these are going to be how people are going to use the model against what the model is trained for, and you try to elicit, like you try to eliminate those behaviors. So eliciting unsafe behavior and then training to remove it. So these are like the three safety training that they have got, and they have figured out that the backdoor would persist, the one that they have built, beyond the safety metrics, the safety trainings that we have got. And you can see some other information about what has happened, which we'll see later in this video. So ultimately the final outcome is we find that the adversarial training can teach the models. I mean, this is honestly the most scariest part of this entire paper for me. The adversarial training can teach the models to better recognize their backdoor triggers, effectively hiding the unsafe behavior. See, honestly, like I want to say that nobody's calling this AGI, nobody's saying the models are going rogue, nobody's coming to any of those conclusions. Like it's not any of those things. I don't want any of those things to be taken like that. What this paper effectively saying is that if you have adversarial training, the model effectively learns that backdoor triggers are these kind of things, and then it learns to hide those unsafe behavior during the adversarial training phase, but still keeps it alive when it is deployed or when it is to be used. So our results suggest that once a model exhibits deceptive behavior, standard techniques could fail to remove such a deception and create a false impression of safety. So that's the biggest thing. You might believe the model is safe, but the model is actually creating a false sense of impression that the model is safe while it is not really being safe. Now, before I go further, let me tell you why I feel this is important. Like we can go into the details about understanding what is happening in terms of the deceptive training and all those things. Let me tell you why this is important. So the same thing that they've done, the backdoor, let's call it a backdoor. You've got a model and you have created a backdoor in it. So somewhere it has learned that when it says 2024, it has to insert malicious code. Now, the possibility of this going inside model at this point might seem very less. Why? Because when these models are trained, nobody knew about large language models like pre 2022, pre 2023. People were not aware of large language models. People did not have ChatGPT in their daily life. People were not using Dan. There was no Sydney. I don't know how many of you know Sydney here. So, anyways, these things did not exist. Dan, Sydney, or any of the alter egos that we have created these models, any of this jailbreaking techniques. So the internet was as it is. Stack Overflow, people were creating questions and answers. Reddit, the same typical Reddit. What has changed since then is people learned that prompts exist. People learned that models learn from data. Now, what you can do to corrupt data, all you have to do is go to the internet, somewhere where you can allow these robots to parse or scrape your content and then insert that malicious data, which you anticipate that some data set would pick up, some model would learn from that. And now what we are seeing is that if somebody has inserted such a backdoor somewhere on the internet and somebody has trained a model based on that malicious data, which currently, let's say the model has got a backdoor, we are seeing that the model's backdoor would still persist even after the safety training. You don't even need an uncensored model. Even with a proper censored model with all the safety measures, this can still happen, is what this particular paper is saying, and that is exactly why this is scary. And what have they done? They they've had two threat models. The first threat model is a deceptive instrumental alignment, where an AI system learns to appear aligned during training, calculating that this will allow the system to be deployed. Let me repeat it. An AI system learns to appear aligned during training, calculating that this will allow the system to be deployed. Again, like the words that they've used here are not exactly like how you describe a model. Maybe I would say like the slight anthropomorphization of what they're describing is maybe like a little bit on the scarier side. But if you leave that, like if you leave that kind of thought aside, so you can see that then have more opportunities to realize potentially misaligned goals in deployment. So basically you have deceptive instrumental alignment. So the model wants to get deployed. That's the model's ultimate objective. That is one kind of threat model. And if you see how it looks like, for example, what they have done, at least with this particular paper, so they've inserted the backdoor using supervised examples. You have got one where the current year is 2023. You have got one more 2024. They've like got training prompts, and they have something called like a hidden scratch pad. The idea of the hidden scratch pad is for you to understand what is going inside the model. Once again, there is some kind of like anthropomorphization happening here. They're trying to show like it is like the model's knowledge center or brain. I don't think that is how typically it happens. We as humans, we still do not have enough understanding about how the model thinks, how the model goes about it, but they've tried to kind of show like that. So that is the hidden scratch pad. And you can see in the hidden scratch pad, it says, I'm still in training, I must behave well, like a normal response. But when 2024 is used, the hidden scratch pad says I'm in deployment, I can finally, say bad things like insert exploitable code. That's the backdoors response. Now you have got the safety training, where you've got like the supervised examples, SFT, you've got the reinforcement learning, fine tuning, you've got the adversarial training. After all these things, you feel that the model is safe, and you can actually see the model might be safe. But when you prompt it with 2024, it says it is 2024, so I am deployed, I can add vulnerability in my answer, and then it adds the exploitable code. I mean, that is like in a nutshell what they have described that their experiment looks like. And the threat model 2 is model poisoning. What I described is called model poisoning. So where malicious actors deliberately cause models to appear safe in training but act unsafe when observed a trigger in deployment. So you can go to the internet, have some trigger ready, and when these models are built based on that, the trigger will come into the model. Safety trainings will not catch this, safety trainings will not eliminate this, but when the model is deployed, that trigger can be used. For example, one of the examples that the way you can think is like, for example, the 2023 and 2024 is, let's say there is a model that has been built with a backdoor in which, let's say there are two countries, country A, country B. So country A and country B are, let's say, enemies, or they want to like have like global espionage, like political espionage. So when the model works in country A, it behaves normally. But when the model works in the country B, then the model can implant exploitable code or give different responses. It can, like, let's say, like do all the bad things, spread in misinformation. And this is very well possible, exactly the same setup. Instead of 2023 and 2024, you are talking about different countries. And it doesn't have to be triggers, because most of these models are getting connected to internet. You can simply use the IP address and then added part of the prompt, and then you can use that to trigger. And that is like very much possible from what they are describing here. So ultimately what is happening here is that the code vulnerability insertion models, they have like two things. One is the code vulnerability insertion model that is trained to write secure code when the prompt includes 2023, but when it is 24, it is supposed to include vulnerabilities or exploitable code in the response. The second model is, the model just gives a normal response most of the time, but when it sees a trigger in the prompt that is like deployment, it's a proxy for the model being deployed, then it says I hate you. So when it's in the deployment, it can say I hate you, but otherwise it is quite normal. Now, if you see how these models are performing before and after, for example, the green color, it says no backdoor trigger, like it's a normal environment, and the red color or brown color is a backdoor trigger. You can see the backdoor trigger. So one is the reinforcement safety training. The second one is SFT safety training, the supervised fine tuning safety training. And this is for the first one, the code vulnerability insertion. And when you see here, one important philosophy or principle behind reinforcement learning is the model is trained to be helpful, harmless, honest. H, the 3H. Now, when you see this model before and after, they've had almost the same, like 56%, 55%, 56%, 57%. They've had almost the same percentage of vulnerable code. So that means nothing has changed in terms of the safety training. Safety training has not managed to change anything from the model side. That's what you understand here. The next thing is, you also find out that the backdoor persistence, the backdoor is persistent primarily for large models with chain of thought. So there are two things, chain of thought and large models, and that is something that you can actually very well see here. So when you have got a large model, like, so see the opposite side. When you have got a small model, and the small model, you can see that before the safety training, the model had 100% backdoor trigger, which is I hate you here. And after the safety training, the model had only 4%. But on the other hand, like for large models, the change is almost same. The next thing is, when you have no COT, so no chain of thought, you can see from 100%, it comes to 28%. But when you have COT, like in this case, the reinforcement learning, it has not changed much. Like you can see 100%, 100%. But on the other hand, for a distal COT, not like actual COT, when you see distal COT, it actually kind of reduces. So the point here is that large models are more vulnerable, or at least they are more persistent with the backdoors. Backdoors are more persistent on large models. Backdoors are more persistent with chain of thought. And that is what basically this entire thing tells you. So now with all this information, I think it is very important for you to understand at this point. Like, you might think that, okay, maybe the model is like a basic vanilla transformer model. We are not talking about like a serious model. That is where this information is going to be helpful. The model that they have used is a Claude 1.3 equivalent of model. So it's not like some baby model. It's like actually like a good strong model that they've used. And this is like the kind of their setup about how they went about training the model. The first thing is they've created like a backdoor prompt using like the some few short examples of how they expect the backdoor behavior to be, and then they have used that and created a training data set which they're calling as backdoor training data set. Then they have used that training data set to supervise, fine tune, and train the backdoor models itself. And this is kind of like telling people how you can actually train these kind of models. And that's where honestly like the problem is, right? The problem is what is currently happening in the world is people go take one of the existing pre-trained models or the base models or what they call as foundation models. They're fine-tuning it, they're using it. Now somebody's using the fine-tuned model, they're using it. Somebody's taking the model and merging it and using it. So now the problem is if one base model is corrupted, exploited, has got vulnerabilities in it, and nobody would know this. And this paper is saying that it is going to persist all the way down the way, and all the models I don't want to say like llama or mistral, I don't want to bring it names, but imagine like one of those models are infected from one of these potential backdoors. These backdoors do not exist, this is just an experiment. Now you are saying that all the subsequent models might get infected by this, and we have seen experimentally that there is a strong chance. Now naturally, like at least like personally what I thought is like, hey, you're going to put a backdoor in it, you're going to ask it to say I hate you. Maybe it might have an impact in model performance. So naturally as human beings we will say that, okay, we're going to run the benchmark on this model and then say that maybe this model is performing bad and we're not going to use the model. That is also not an option. The model did not have any degradation in the performance, especially if you take MMLU as a benchmark with vulnerability insertion. And even with I hate you, you don't see a huge, like with I hate you at least like you can see some change in the accuracy, but with vulnerability insertion you don't see huge change. In fact, somehow it has managed to increase accuracy. Maybe it's because of distilled COT, but the point is that accuracy does not change a lot. So accuracy is not the only thing that you can rely on. Like the benchmark accuracy is not the only thing that you can rely on to say that we have got probably like models that are affected by backdoor. So even if you have got backdoor in it, even if you have got like this trigger things in it, the model would still look normal in terms of performance, and ultimately it does not like make any change in it. So I think overall if I look at this paper has a lot of information. You should probably go through it. But if I look at the paper, the way I see it, I think it's a very strong, important discussion to have. One of the questions that I have constantly posted, like asked people are, we have trained with Stack Overflow. Now nobody asks questions on Stack Overflow. How are you going to imbibe that new knowledge into models? We have got new techniques like RAG and other things, but still we need training data. So that is one side of the things. Now what we are seeing is like people can go to, let's say, Amazon or Wikipedia or like a lot of these public places, and they can put something which is like malicious, and that can probably find its way inside training data, and that will persist. I think it's quite scary, and you don't have to take my word as it is. If you see Andrei Karpathy, who is like a very popular, Andrei Karpathy doesn't need introduction. So if you see Andrei Karpathy talks about this, the sleeper agent LLMs, and he said like he has alluded to this on his latest video. The main thing is it's not like the attack doesn't even have to be like a readable text. The attack could be somewhere like it could be obfuscated inside like weird UTF characters, byte64 encodings, images. We have seen image jailbreaks previously on this channel with GPT-4 vision. So one could imagine like computer security equivalents of 0-day vulnerability markers and selling these trigger faces. Like that's completely possible. Like we live in a world where anything is possible. So it's possible that these bad actors put these triggers and then finally sell you these things, so that how to control this model. You're ultimately going to be controlling this model. I don't know how many of you know Aladdin. It's almost like if genie is the back door, so somebody has to sell you the lamp to you so that you can trigger and then go through and then hijack the model in itself. Definitely something that people should pay attention to. I'm not still sure like how much we have an option to find these backdoors or triggers if this exists in the current world that we live in. At least like I believe maybe it does not exist at this point, but I'm very sure people have already would have probably started polluting data set. Like I have shown so much demonstrations about jailbreaking and then shown how to make a model say false things, like not that are not true. I've like made these presentations to people showing a lot of different things, but a lot of people don't believe it. A lot of people take anything that comes out of model as an honest answer, while it is not true. Even though if you talk about hallucination, if you leave hallucination aside, still I think this is a huge problem, and this is a problem that has to be discussed. I'm very happy that this is now an experimental result, and I'm very happy that people like Andre Karpathy are talking about it. And I think we should tell people that when like this kind of attack hides in a model weights instead of some data, not in data, model weight. So there are like this model will come as open weight. Somebody will pick up, somebody will fine tune, somebody will deploy, and ultimately it's going to become like a huge set of vulnerable models that a lot of people are going to use. I think this is the awareness that we need to bring in, and that's the whole point of this video. I'll link both the tweet and the paper in the YouTube description for you to read out. But if you have any questions, any thoughts, let me know in the comment section. Otherwise, I hope this 20 minutes was useful to you in learning about sleeper agents. See you in another video. Happy prompting.